All right. So you can dwell on how I did that magic trick in your spare time. All right.
So it's multiplied by 10. 100.
Don't give it away though. That would be so much. That's like magician's code, right?
Can you do an x value other than 10?
Of course. Yeah.
Why did you do it? Let's do 2.
Well, I just because I do it. Just my magician's prerogative.
Oh, I know how to do this.
All right. So we're going to start a new unit today. Unit 2 is what it's called, polynomial and rational functions. And I have, like, just to kind of continue with the magic, I have really a remarkable story about this unit and something I saw recently that you're really going to be astounded by. I went down, this was like late at night, okay? You can picture this because I was working late. I often work late. And I was grading some quizzes, something like that. And I was like, man, I'm getting so thirsty. So I went down to one of those vending machines down by, in between like the main office and the auditorium. And out of there, I was looking for a Mountain Dew, but I pushed the button, and that is not what I got. Okay? I put the correct amount of money in. I swear, I pushed the correct button. And this is what I got instead. Okay, are you ready? No, no. Wait till you see it. Wait till you see it. Wait till this button works here. Let me show you with this. Okay, this is what I got out of the machine. It was just remarkable. This was just a couple weeks ago, and just to confirm, I was like, maybe it just dispenses these. They put them in wrong or something. I pushed the button a couple more times, and I got Mountain Dews. It was just like a one-time fluke. You may not go down there now and get one of these. It's like a one-time thing. I put it on a white piece of paper with a really even light, and then took a photo and put it into our PowerPoint. And then I also added this link to like kind of like throw you off. Exactly. Okay. I think maybe because there's corn syrup in it. I don't know.
Is it corn flavored? You drink it?
Maybe it's corn flavored? No.
Wait, I need to take a picture.
But isn't it amazing? It said not only the name of our unit, but also I'm pre-calculus fine. I was just amazed by that. I thought that was just startling. I had to show it to you, you know. And the whole story is true. Yeah.
Does that mean that for Unit 1 your whole movie thing was fake too?
Oh, wait, what? No.
No, they're both real, Lucia.
They're real. All right.
Oh, I didn't know it was first
No, the first one's real, Jeff. That one was real too.
They're all real.
Chase doesn't lie.
I don't lie. I stand up here and all I do is produce truth for you. That's all I do. Okay. All right, here you go. Let's talk about some polynomials today, and as we go deeper into polynomial and rational functions, hopefully that will be in fact what we do. We go deeper for you. As usual, make a note of your homeworks and your assessment dates, the 3 on the bottom of that yellow sheet, and the usual disclaimers apply. Tonight, homework 1. All right, so let's start by talking about a couple things here that might be a review. Let's think about end behavior first. It's a concept that we talked about first in Unit 1. But now let's say what it is for polynomials. And by polynomial, I mean something of this form. If you were to ask someone what a polynomial is, they would probably say a couple things. What do you need? Well, you need positive integer powers on all of the x's, okay? And unlike the warm-up, these coefficients, which I'm naming a sub whatever, all those coefficients can be any real number at all, right? Positive or negative, anything. Notice that we're using a sub n to mean the degree, to mean the coefficient on the nth degree term. So, like if this is a 7th degree polynomial, then n is 7, and a7 is the coefficient on the 7th degree term. And going downward. Now, if this is a 7th degree polynomial, does it have to have like an x to the 6th term? That seems to be what this says. But that's okay, because then what would a sub 6 be? If x to the 6th doesn't appear in your polynomial, then what's the coefficient on it? 0, right? So we're okay with this still. Just a6 would be 0. All right, and you're okay with this triple dot notation, hopefully? And notice, too, that a0 is kind of a coefficient, but it's really just the constant term. If you want to say it's the coefficient on x to the 0, you can, but, right? So just to be consistent with the notation, though. Is that okay? I think you've maybe seen that kind of notation before. And then speaking of notation, in the last unit we talked about this limit as x approaches positive or negative infinity notation. So let's use that again here. And what we're saying is the end behavior is completely determined by the first term, by the degree and by the leading coefficient, which is, again, I think not news to you. Let's just review. How do you get these 4 pictures? And these are the only 4 pictures that you could have with a polynomial. I'm not talking about the little wiggles here in between, right? That might be up for debate. But out at the ends, all a polynomial can do is this, or this, or this, or this, right? So tell me, from the leading coefficient of a polynomial, this is, I think, review. You tell me. Can you tell, right? How do we know that, like, give me an idea of what this first one would be like here. What are we looking for to be true about the polynomial? How do you see one of these coming? Just if I hand you the polynomial. Someone say like you mean it though. Where are you? Come on, someone. Not all at once. You're overwhelming me. Yeah, go ahead, Peter.
I think it's positive and odd.
Okay, positive leading coefficient, odd.
Odd like X.
Oh, odd degree is what we might say. Yeah, exactly. So, yeah, correct. Yeah, this first picture is if the leading coefficient is positive and the degree of the polynomial is odd, 10 imaginary bonus points for Peter. Okay.
Oh, I remember this.
What about this?
That would be odd, and if it was negative.
Yeah. I'll put that up here. Someone else get the next one? What's going on there? Yeah. Jen.
It would be if the coefficient is positive and the
Right? And then the last one is the case that no one said yet, and that's, of course, if it's even with the leading coefficient that's negative. All right, so that's what these boxes say. And we have the technical limit notation to describe this picture with a little more precision than just the picture. But again, maybe new notation, but no surprises here, I don't think. Yeah, am I right? Things you've thought about a little bit before. Okay, I should have warned you early on that we're in just in a very short time here. We're going to have a dance party. Well, you ready? If you don't finish this slide right now, like copying everything down, remember that it's on that. I put all the PowerPoints on that line already, by the way, if you want them. And just remember it's also in your book. And remember that even if I go off this slide, I think you can fill in the gaps. Like if I didn't write down the last box, I think you can fill it in. Yeah. Right? Whatever. No. Or you take it. Oh, that's it. Whatever. It's all good. It's all good. I don't understand why this is necessary. The PowerPoint is on deadline. Didn't I just say that like 2 minutes? Okay. I'm ready now for a dance party. Are you? Okay.
Yeah, I didn't know it was there.
All right, so let me educate you a little bit on how we do this, okay? I'll do it solo, but in about 10 seconds from now, I'm going to make you stand up and do this, okay? Just warning you psychologically, like, so that you can be prepared for this. Are you ready? Okay, so I'm going to say a number, and by the number I mean the degree, and then we're going to do positive leading coefficient, negative leading coefficient, but I'm not going to tell you those. So it's going to go like this. So I'm going to say 1, and we're just going to do positive, negative. 2, 3, 4, 5, and then you just kind of start feeling that beat. 6, 7, 8, and what else am I doing? 9, 10, 11. Yeah, they get a little skinnier maybe too, just for fun. Okay, right? You know that about maybe polynomials they do. Are you ready? All right. You all are required to do this.
There's no like change step. It's not white.
Yeah. I think you'll be able to handle this.
There's no like turnaround.
Yeah, you can add those things on top of it. Okay, are you ready? As we go, we'll also get just a tad faster, okay? Because we want to work out the rhythm. All right, are you ready? Here we go. Ready? 1, 2, 3, 4, 5, 6, 7, 8. Did I just do this one? 9, 10, 11. Are you having fun yet? 12, 13, 14. Keep doing it. 15, 16, 17, 18, 19, 20. All right, we're gonna do it again. All right, this time for real. Are you ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 30, 48, 62. All right, why don't we do these? All right. Good job. Yeah, get yourselves in here. Towel off after that. It was intense. Who said it was like Zumba or something? It is exactly like Zumba. It is exactly like Zumba. That's right. Exactly. Okay. All right. Let's work on these 3 fabulous problems to deal with. Well, possibly deal with end behavior. Let's see.
Oh, that was good. Say that one.
Okay, so the first one's already got me kind of in a bind. So can everyone stare at that until they can figure out how they're going to help me? Now don't look at the graph, right? We're trying to just look at this, the form of this equation from the algebra and what we know from the last slide. Can we tell me something you know? I mean, help. What do you know? Okay, why? Yeah, even though it's not written in standard form, you can tell this is a 15th degree polynomial, can't you?
Yes.
All right, so it's got to be one of those 2 cases. We've narrowed it down. So now, our only task left is to figure out whether the leading coefficient is positive or negative. You got something for me, Aaron? What do you think? How do you know?
Yes, good job.
How do you know?
Okay, because the coefficient outside negative 15 and you in parentheses x is negative. So if you multiply it out, it will be 15x power and so on.
It'll be like a lot of stuff. I think you're actually suggesting we multiply it out.
No.
That sounds like fun. Let's do it. Okay.
Eric, don't be that person.
Oh, we just need the first leading coefficient? Okay, so, but we can at least think about it. This means 15 minus x. 15 minus x. A whole bunch of those. 15 minus x. Okay. So I think you're saying... All right, this is the debate. I mean, it's laid bare for us now, isn't it? All right. It's positive. It's negative.
It's positive because the exponent is odd, so you'll end up with negative x to the 15th times negative 15. That's a positive number.
Say it again, because no one knows listening.
It's positive because you'll end up with negative x to the 15th power, which is times the negative 15, which is a positive number.
So this will all be negative x
15.
to the 15th,
That would be, yeah.
plus some other stuff here.
Plus a lot of other things.
Like a lot of stuff, right? And there's like an x to the 4th term. In this big expansion, if we were to actually do the multiplication, there would be an x to the 4th term. And there would be an x to the 13th term. But we just don't care what the coefficient on any of those is, right? So I think if you agree, do you agree with him that that will happen? If you multiply all the negative x's together?
Or you can just make it negative x plus 15, and you know that it's a negative. And they're both negative, so it turns into a positive.
Say that again.
You can just make it negative x plus 15, and you know they're both negatives. So that turns into a positive.
Yeah, so what's the reason that comes out to be positive, this comes out to be negative? Well, it's because of the 15, I guess, up there, the exponent, right? Like if this was a 16, then the leading coefficient would be negative, right? Do you agree?
Yeah.
Okay. All right, so I think the game is up. So the limit behavior, we can just write it down here now. That was like the hard part, is the algebra. So as x approaches infinity and as x approaches negative infinity, this is odd, right? Odd degree. So what are the answers there? What are the answers? Just shout them out. The first one's infinity, and the second one, this is the right hand behavior. And down here, negative infinity. Okay. Whew. Isn't that a fun problem? I like that. Not in standard form, so that kind of maybe throws us for a loop in this crazy factored form. Talk to me about the next one, someone. Who's got that one? Wait, no. I'm going to call on someone. I'm going to call on my favorite student. Rapid, go. Whenever you're ready. Excuse me. Let me give you a minute.
Hey.
Let's really think about it. And then you finish.
Talking about favorite students.
My favorite student of the moment. Because I pick him out of the thing. Yeah. What is the answer to this question? That's my question. If you're ready. What do you think? Tricky, or at least, what do you see? What do you know? Tell me what you're thinking. All right, everyone take a second to talk with your group. Make sure that, like, you guys,
Even negative.
what do you think?
Even negative. It's even negative. It's even negative. It's even negative. Because it's negative 2x. You already know.
All right. That's more than a second. We're wrapping up. What do you think? Listen, guys, come back together. Yeah, what do you think? Why? Yeah, it's fourth degree. Do you see it? We're trying to trick you up a little bit by putting it out of order, but you see it. Fourth degree and negative leading coefficient. The answer is negative infinity. Yeah, as x goes toward negative infinity, y approaches negative infinity. If the question was infinity instead, it would still be negative infinity as the answer, right? If this was positive. Okay, let's move on to the next question, which seems to be switching gears a little bit. Wait a second. What? What?
Oh, because it's to the cube.
I have no idea what the solutions to this equation are, but I do know there must be one. Why? You want this one, Isabel? Talk to us. Okay, go. Are you trying to guess a solution right now? Yeah, good luck with it. All right, yeah. But yes, that would be true. If you could do that, then I agree. But I don't think that's going to be easy or possible. You know. Yeah, Judith. Yeah.
Approaches infinity and negative infinity and it's continuous.
Okay.
It has to get 0 at some point.
Oh, what a fabulous little proof. Okay, I like that. It has to go. Now, what are you talking about? It.
Okay.
What function?
If you subtracted minus 12.
Are you gonna move these things over?
Yeah.
Okay.
Then you've got x cubed plus 2x squared minus 12 minus whatever it is that x is.
I got you.
Then we can like. Okay. So if we make a function y equals that.
Okay, so this is now called f.
Yeah. Then we know that it approaches infinity and it approaches negative infinity, and we know the polynomial is continuous, so it has to hit 0 at some point.
Okay, I love the fact that you invoke the continuity of polynomials too. That was cool. Yeah, do you want to add something, Reeve?
Since it's an odd,
Yeah.
to pick the
Yeah, thanks for adding that extra bit there too. Anyone else want to say something about it? Absolutely, I love what all of you are saying. Yeah, so one explanation or another of the type that you just heard is great. You can write it down in English words. You could also just say the range of any odd degree polynomial is all reals too, if we take that as a given. But maybe the reason we know that is because of what, like Judah said, though. Maybe that's the reason that that is true. So, whatever. You could explain that in a couple ways, but okay, I won't write it down. But write something like that down, maybe. You could talk about the end behavior. It's not true for a fourth degree polynomial, but it would be for a third degree. Speaking of zeros, let's talk about zeros. By a zero of a polynomial, we mean solutions to the equation f of x equals 0, right? Or sometimes we also call them, since I guess they're important and we like to have lots of names for important things, sometimes we also call them X-intercepts or roots. For the most part, those are interchangeable words. So when you're ready, demonstrate to me that you remember. This is like summer packet type problem. In fact, it might actually be. In fact, it might be exactly like one of the ones on there, I think. Find the zeros of this. Go, right? So, in like, I don't know, 20 seconds from now, I'm just gonna have someone give the answer, and we're not gonna show work maybe either, and we're just gonna move on unless someone wants to see the work. Just take a second to refresh your memory on finding roots.
Oh, that's cool.
Is it cool? All right. Bless you. Bless you. Bless you.
It's 0 and 5. No, it's 5.
Okay, in 5.
X minus 5 and X minus 5.
All right, 0. All right, let's go. Goodell, what are the answers? What'd you guys get over there at the freshman table? Did you get 0 and 5?
X equals 0 and 5.
I'm sorry, that's correct. Yeah, good job.
Yeah, there's a double.
First one in this class.
All right. Is that cool? Is that cool? Do we need to say any more? Do you need to see work? I think ask someone at your table if you need some more work there. The work actually would only take me like 2 seconds to write, but we'll just assume everyone knows that the answers are 0 and 5. I think everyone knows what the y-intercept of a polynomial is. The y-intercept is also known as the constant term, a0, is what we called it on the first slide, a0, the constant term. But this isn't written in standard form. Oh no.
Oh no.
But that's okay, because we still know that for any function, no matter what it is, polynomial or otherwise, the y-intercept is the value of y when x is 0. So, thank you. All right, good. So tell me someone what the y-intercept is. In a second, don't yell it out. I'm going to call on someone. When you're ready. Where is Alex? Alex. Are you Alex? Sure. No, you're not Alex.
His nickname's Travis.
Alex. Go ahead. All right, Alex, when you're ready. Are you ready?
I'm really bad at
No, Alex is supposed to do it. I'll give you a second. Everyone's still working.
Wait, no. Oh, I'm sorry. No, I'm sorry. I thought it was minus side. So.
All right. Are you ready, Alex? Plug in 0. Tell me what you get.
Plus 2 is 2.
Have to plug in 2.
We're multiplying out all the the square does not apply to all the parentheses.
True.
Yes, it does.
No, it doesn't.
No, only the numbers matter.
I want to know where we're at.
Because you
What'd
square
you get? What'd you get? What'd you get? Negative 12, yeah. All right. Come back together. Alex has an answer for me. Shh. Listen. Did you get what he got? All right, good. I don't have anything else to say. I don't have anything else to say about y-intercepts. Let's talk about multiplicity of zeros. Okay. All right. Yeah, some of you might be familiar with the idea of like a double root, like what happened on the last problem, for example. 5 was a double root. So this generalizes that idea. We use the word multiplicity to capture that concept.
So why do you use square?
So if the factor, say, x minus 5 to the second appears, then 5 has a multiplicity of 2. So in this case, if x minus c to the m appears in your factorization, then c is the root of your polynomial with multiplicity m, if you want to like generalize the idea, right? Now you might be like, that's neat. I'm glad we have a word for that. But we can actually say something pretty significant about the behavior of the graph around that particular zero of the function. If the multiplicity of your polynomial, of your root that you're looking at, is odd, then the function will cross the x-axis there. Maybe that's not a huge surprise. You're like, of course it has a 0 there. But if m is even, then what do you think I'm going to say? It has not crossed. Then what does it do? I don't know. What would you describe it doing? I mean, it certainly still has an x value, has a 0 there still. Bounded at that point. I mean, it's not, the whole function isn't bounded, but it's bounded there. Above or below. Here's how we'll say it. This is not super mathematical maybe. We'll say that the function touches the x-axis. Is that okay? So it has a 0, but it doesn't actually change sign. Like the y values were positive. As you cross that 0, the y values are still positive then. Or they're negative and then they're negative again, right? They go up and touch 0, but they come away. Yeah.
Can we say that it's a local or it's a local minimum?
It would be a local min or max then too, yeah, absolutely. Yes, very astute. Now, if you don't like that language, I have actually maybe a more technical way of saying it comes from the book. Let me make sure I get this right. The wording is really important. Let me make sure I get this right. Okay, wait. Okay, so section 2.3, polynomial functions of higher degree. Okay, so page 205, if you're with me. Okay. Notice in figure 2.27 the graph of f. So you can use their word if you want. Notice in figure 2.27 that the graph of f just kisses the x-axis without crossing it. So I'm not lying.
Why?
Page 205.
Why are they putting this language in our? How are these people allowed to like this is outrageous? And we're wondering why China's ahead of us.
I know. So the point has been captured, hasn't it though? Comes down and hits the x-axis and then leaves again without crossing it. Okay. So let's actually try this with combining all of our knowledge here. Okay, so help me out with this guy here. I want to know everything you know about it. So where did it go? Where's my super pen?
I think you put it on the desk over there. That desk over there, maybe. When you're talking.
I know, I'm easily distracted.
Or at the board.
I might have thrown it away.
You should
How
buy
can we?
extra.
I should. Anybody see it?
Guys, is it on someone's
Oh,
desk?
it's right here. All is well again. All right, so tell me anything at all that you know about this function on this list maybe. Yeah, go, Eric.
The Y-intercept is 4.
The Y-intercept is 4. Okay, if you plug 0 in, you get 1, 2, 3, 4. Okay. You all agree with that? Tell me something else you know. Go ahead, Sean.
Yeah. The function touches that.
Okay. Where? At 2. Okay. 1, 2. So there is a 0 at x equals 2 with multiplicity 2, which is even, therefore it touches it there. We'll draw it in a minute, but when we do draw, we'll keep in mind that it just touches, it does not cross there. Who else I haven't heard from recently? Peter, okay.
It also touches the x-axis at -1.
At -1? Okay, and
Or cross
it actually crosses it there. Yeah, exactly. So it can actually cross over there. All right, what else do we know? We're doing really well. Yeah, we know, what about end behavior? We know it's an odd degree polynomial. I hear some people muttering over here. What the leading coefficient is positive, so therefore it looks like da 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 that, okay? Yeah? Looks like that. Create the shadow on the board. So I think I'm ready to do it here. Are you ready?
Yes, that's what I got.
Something like that, maybe? I don't know. It's not perfect. It's not perfect necessarily, but it does capture the things I said to take into consideration. One thing in particular that I wanted to make clear is that, like, this is not necessarily, it'd be tempting to maybe make this right here the maximum, which maybe it is, but maybe it isn't. We didn't say that necessarily, so we shouldn't, like, assume that that's a local maximum necessarily, okay, when we draw it. I won't take off if you, like, picture it that way, but we just don't know that. We don't know enough information to talk about maxes and mins really yet. Wait for calculus, as usual. Wait for calculus. I know everything's wait for calculus. Anything else you want to say about that? At the very least, we should be able to walk away with this. Listen, guys. Thanks. We should be able to walk away with this kind of, from this feeling pretty good about the fact that this is like a cubic, and I just know a lot of information about that even without a calculator. Like, I'm pretty good at understanding its behavior and what it's doing, its x-intercepts and y-intercept without a calculator. So let's try like a slightly trickier one as we close out today. Okay. So again, let's play, we'll start at least to play, what do we know? Give me something, you know. Yeah, Tim.
touches the x-axis at 4.
Okay, so wait, let's see here. We got a 4. 1, 2, 3, 4 is a 0 of this polynomial. And -4 is 2?
Yes.
Because it makes this 0?
Yeah.
Okay, because -4 squared minus 16 is 0. Okay, I got it. 1, 2, 3, 4 is a 0. Any other zeros we want?
Actually, positive 4 is when there's more than one 0.
Yeah.
Squared minus 16 is plus -4.
Okay. What we're missing a 0 though? Yeah, 1 also is a 0. Okay. Oh, I'm sorry, 1. We say 1. Not -1. Just 1. There we go. Okay. What else do you know? Now, before we go too crazy on this, maybe we try to clean this up a little bit. Maybe we'd like to actually factor this like you were saying, and maybe. Yeah, you have something to add, Judah? Yeah, exactly. Let's maybe actually rewrite this here a little bit, just because it seems like people are doing that already. So let's actually do it. Okay. One thing we could do is we could say, let's not go too much further without, we could say what the y-intercept is. What is it? 16 times -16, which is -256, right? Okay, so 1, 2, 3, 4, -256.
2048.
Okay. What else? All right, are we? I'm interested to return to the question of what's going on with the. Well, yeah, we could talk about end behavior. I think we could do that without too much more work. Let's see. End behavior. What's the degree of this thing?
It's
Oh my.
odd and it's negative.
It's 7th degree polynomial. Okay, so this is odd again. The leading coefficient is. Yeah, we're gonna have this will be a -t to the third once we multiply it out. This will be a positive t. This will be a positive t, and this will be a positive. So it's negative leading coefficient.
Yep.
Okay. So yeah, all right. So we have this this shape again, going downhill, kind of whatever you want to say. We have that end behavior case. Let's return to the question about the multiplicity because I'm a little confused about that. what is the multiplicity of -4? At -4, it's pretty clear that only appears once. 1. Right? At -4. At 1, the multiplicity, I'm pretty sure, is 1. But what about at +4? What's going on there? Oh, it appears twice? What about this one? Yeah, so talk to me about this algebra going on here. What is this? And what is this? I mean, what is this guy? I'm not used to this. 4 minus t squared. All right, and stay with me, please, till the end. What is 4 minus t quantity squared? What is that? I mean, you're not used to writing it that way. If you actually multiply it out, yeah, you get t squared minus 8t plus 16. All right. So, is that normally how you write it?
Yes. That's
I claim that those are the same, right?
Because they are the equivalent of -1 times the other, and you can square it anyway.
Yeah. Can you prove this? You might be able to prove it a couple ways, but one way would be to like multiply this out on the left, multiply it out on the right, and see that they're the same. Okay. So I'm just trying to like mess with you is the point. Okay. All right. Shh. This is the moment of truth. Okay, don't miss it. So this has multiplicity 3. These have 1 and 1. So actually, in all places, we have a place where it crosses, right? A multiplicity odd, multiplicity at all. Okay. So are we ready? Let's see if we can do this. Something like this. I don't know. Something like that, right? It's probably not perfect, but we'll go with it. You can graph it and compare. Remember, we're doing homework 1 tonight? Okay. Hopefully we've blown your mind today.